I know we are not completely done. We're going to go over this. Remember, your test will reassess these skills, so we need to make sure we are focusing on this as a learning opportunity. So all pencils completely off the desk, and then pick up a pen, take whatever notes you need to, ask whatever questions you need to ask. I'd already started recording. All right. It helps when I have the presentation note ready to go. I promise I'm on top of things today. All right. So, first off, don't forget why we are here. We're here to learn, we're here to grow. I'm having to move quickly because we have a test on Monday, so we're going to go over a couple of things, but you're capable of amazing things. The only way you meet that, though, is through growth and learning. Note about the test, be aware that the formatting is going to go back more to that traditional formatting that I did with the first couple of tests of there's a short answer portion, a non-calculator portion, and a calculator portion. Because just like with the assessment we just did, if I gave you a calculator with number 2, you could just type that into the calculator. You would have seen what the end behavior was without having to think through what the end behavior is based on the equation. So there will be a non-calculator portion of the next test. Something else I do want to point out. Good morning, sir. Just grab a pen and take notes on the understanding check. Were you getting this signed, or getting this excuse done? Is that what you're late? Okay. Is this for yesterday? Okay. All right. Here's a pen for you. Here's this signed. Oh, did I already put a pen out for him?
Oh, I did too.
Wow, you took Naisha's pen. All right. So one thing I do want to point out is when it comes to the unit that we are doing right now, it is actually very, very heavy in terms of vocabulary. Things like relative maximum, relative minimum, extremum, end behavior, polynomial, fundamental theorem of algebra, all of those different things. One of the things I do when there's a very vocab heavy unit is I will actually give you somewhere like 8 different vocabulary terms on the test. And what I'll ask you to do is pick 5 or 6 of them, and you have to define it, you have to give examples of it, and you have to explain why it's important. So be prepared to know what those vocabulary terms are that were bolded in the book, that we talked heavily about during lessons, things like that. Vocab is an important part of this unit. If you don't know your vocab, then it makes things hard.
So you're going to take a math as vocabulary test?
You're going to take a math test, but to show me mastery of your mathematical understanding, there is vocabulary as a part of the test. See, this is why we struggle in math, because we don't know our vocabulary. So, this is actually not to punish you, it is more designed to help you think through the most important things. Like if you don't know how to define what the degree is and explain how to identify the degree, then that's a problem. So, that might be a vocabulary term. End behavior is something you have to know for this unit. So study that end behavior, be prepared to define it and explain it, things like that. So it's actually more designed to help you prepare than anything else. Okay? So be aware and look and prepare by studying that vocabulary. That's the conceptual understanding that drives all the procedural. Literacy for all, I'm a failure of a teacher in that regard. I will have it back to you on Monday, especially for those seniors who need to update and resubmit by Friday. And so I will take Literacy for all back on Friday for seniors. For the juniors, you have a little bit more time, maybe a week and a half to update and resubmit if you need to do that. So I will be giving you back your Literacy for Alls. I will give you back the graded version. I will email it to you if you send it to me on Schoology. Now let's have this understanding check discussion. So, before I actually show the answers, which I accidentally already did, number 1 on this understanding check, what degree polynomial did we think we were looking at? 6? I heard 6 pretty quickly. Is this supposed to say 421 through 425? It just says 421 and 425. You know? Okay, I'll check on it. but here's this back, before I mark it in the book. So, 6th degree, I heard that pretty quickly. Why are we thinking 6th degree? There's 6 points on the x-axis. Anybody want to push back on or add on to that level of detail?
I was saying that they were only 5.
Okay? This one say Mr. Kennedy? Yes, ma'am. Huh? Go ahead and finish with the, finish it in here. We'll be talking, but without just, huh? It's gonna distract. I mean, you can pull a desk out into the hall if you need to, but we're gonna start going over this. Okay, so 6th degree, but Lily-Kate, you're saying you only saw 5 x-intercepts, so you were thinking it'd be what degree? 5th degree. Anybody have any other evidence that they want to add on to or push back on with number 1 here?
Double root.
Okay, so it had a double root somewhere. So what degree did you think it was?
6.
Okay, so you saw 5 x-intercepts, but you saw a double root, so you said it was a 6th degree. What do you think about that, Lily-Kate? Does that make sense? I will point this out. This is something else you want to think about with this graph. Does anyone see another detail that tells you it cannot be 5th degree? That end behavior is the same, right? So if that end behavior is the same, that's something we do want to note, that it has to be what type of degree? Even, okay? I'm going to show my answers in a second. Number 2, as x goes towards negative infinity, what did y go towards in number 2? What are we thinking? Any ideas? Or are we lost on this one? So on number 2, 2a specifically, with r of x, as x went towards negative infinity and as x went towards positive infinity, what's your y going towards? Remember, that's what I mean by end behavior. You stuck on this one? Say again. Okay, so let me point this out. We have r of x there. What do we know about r of x just looking at that equation? There's 2 things we got to know to figure out end behavior. Okay, the highest power is what? So the degree is 7. Why is that important? It's an odd degree. So what does that tell us about end behavior? It's going in different directions. Well, remember, what's the simplest odd degree polynomial there is? First degree, which is a linear, right? So it's either got to have this end behavior or it's got to have this end behavior, right? That's a linear function. Those are the 2 different end behaviors for an odd degree. So which one would it be? The first one, the one on the left? Why is that? A, the leading coefficient, is positive. So as x goes towards negative infinity, what's y going towards? As we go to the left, it's going down towards negative infinity. Please notice, this is not at all what x to the 7th would look like, but it would have that end behavior. That's something that I can picture in my mind right away when I see an odd degree with a positive leading coefficient. And so what would be the right-hand end behavior? Because notice every graph has both left and right hand end behaviors. So as x goes to the right, what's y going towards?
Positive.
It's going up towards positive infinity. That's what we have to notice, right? You need to have 2 end behaviors with it. So I'm not going to draw the next one up there. I'm just going to go to the solutions that I wrote out. But what then should we know about b, g of x? So the end behavior has to be the same because what degree is it? 4th, or just at least even, right? And the end behaviors would both be going which direction? Be going down, right? Leading coefficient is negative, so it's going to go towards negative infinity. So please notice, when we talk about end behaviors, how many end behaviors do you need for every function? You've got to have 2 end behaviors. You have to have 2 end behaviors. You have to have the left-hand side, you have to have the right-hand side. Jalen, you taking notes, learning from this discussion? Looking at my notes, Z, or anybody else, what questions do we have?
What's the word after the same?
Where?
After the same.
Oh, even degrees, so same EB for in
Number
behavior.
one.
Oh, what does that say? Same in behavior, so it has to be even. EB, anytime I say EB, it's in behavior. Right, so that's what I was noting earlier, right? So we should know it's not fifth degree, which I totally get Lily Kate's thinking that because that's 5x intercepts. But, right, same in behavior, so it had to be even, it's because we had a double root. Ooh, I misworded that. It is not at least 6x intercepts, that's at least 6 what? Roots or zeros. There's only how many x intercepts? It's only 5x intercepts. But that x-intercept has a zero as a double root, so that's why it's 6 zeros in the 6th degree. So, questions, comments, concerns. Questions like these will definitely be on your test. You'll see questions like these on your study guide that I gave you yesterday. Triana, who else? Jose, who else was not here yesterday? Was it just you two? Okay. So, I passed out a study guide yesterday for your test. No. Somewhere around here. There's one of the pages. Alright, now that you'll have a little bit of time to write stuff down, what questions do you have before we continue? Going once, going twice. Trailing, you know that is there not a copy of the understanding check? Right here, so that you can take notes, do something with it. Alright. Next question was asking about the number of extrema. I think that sounds right. What do we know about the number of extrema for that function? It's the what? It's the number of turns. So extrema, number of turns, the max, the min. What else do we know? How do we figure it out?
Yesterday I didn't recite someone about
So it's 1 less than the degree. Okay? And so that is all I would expect out of you, just to help your understanding improve. Do notice that that is, remember, the maximum number of turns. What pattern do you see, though, in the other options?
These other reasons.
Could be double roots or anything.
Okay, so it's not necessarily the double roots that are going to affect us. Triple roots will, which sounds, I know, bizarre, and imaginary, but the bigger thing is, so like here, a 5th degree polynomial could have 4, that's the maximum, but could also have 2 or 0, so the number of turns always goes by how many? 2s. So it starts with that maximum value, and it always decreases by 2. Okay? So like a 5th degree, we actually looked at this yesterday, when we had that power function. Remember how it flattened out really heavily in the middle and then got really steep on the sides? Notice how many turns does a 5th degree actually have here? 0 turns, right? So it can go down by 2s based on the number of multiple roots or the number of imaginary zeros. Okay, that's why with the 6th degree it could have 5 turns or 3 or 1. What questions do you have about that information? And again, please notice, when I collect these and make scans, I'm only looking for the maximum number. Now, please note I did not justify that. I should have. What justification could I have put here to explain why 5th degree has 4 and 6th degree has 5?
It's one.
Say again.
It's
It's one less than what?
the
The degree, right? So that's something I'll be looking for, is that the maximum number of terms is the degree minus 1. Okay, this next part required you to apply things that you do know, and I reduced the characteristics from what I had students do last year. This one would have been a little bit more difficult, but this is a good discussion point and something I will be expecting on the test because we'll be practicing it today. Notice there's actually 2 options that I have drawn with A. Notice it had to have degree what? 4, and it had to have how many roots? Or 2, I should have said 2 x-intercepts is really what I should have said there. It has to have 4, no, it could have 2 real roots, that's fine. Notice here, we actually have 2 x-intercepts, but how many terms do we have? 3. So it has to be 4th degree, so where are the other 2 zeros from this blue one? They're imaginary, right? That's what we want to notice here. Technically, when we say 2 real roots, that means we'd have 2 x-intercepts and then 2 roots that are imaginary, and this would satisfy that because it has those 3 extremas, so it'd be degree 4. Notice the end behavior as x goes to negative infinity. What does f of x stand for again? Y as to be going towards positive infinity, so both had to be going up. That's what we'd want to notice there. I would have accepted something like this pink one, although it's technically not right from the 2 real roots. It could work with 2 x-intercepts. Why would this pink kind of work? I don't have imaginary roots here. What do I have? I have 2 double roots, 1, 2, 3, 4, 0. So that would still be 4th degree, but I would have 2 double roots. And so that is matching those characteristics that I am looking for on this assessment. So notice it's just taking characteristics that you know and applying it by sketching out a graph. There's lots and lots of ways to approach this. Just you can't break any characteristics. So could I have the quartic going down? It'd be going down like this. No, because of the end behavior requirement, right? Could I have had the end behavior going in different directions? No, because then it wouldn't be an even. Could I have had 4 x-intercepts? So could I have done this, where it goes like that? Because that would be 4 real roots and not just 2, right? So those are things to be aware of. I'm looking for you to match or identify those characteristics. Notice I did not draw anything for B. Why is that?
It's possible.
Why is it not possible? There's a couple of reasons actually.
It doesn't give you like the number degree or the amount of roots.
So that's, you can still work with that, right? Like that just means that you have a lot more flexibility with it, but there is something that breaks when we look at multiple of these
They
characteristics.
can't go from negative to positive back to negative.
Well, be careful, right? So this is not going negative to negative. Well, this is one end behavior, so to match that, it has to do this, right? And then it would have to do this to get back to going towards negative infinity. What's the issue with that graph compared to the other characteristics? Right, it has to be an odd degree, but this graph would have to be what? Even degree. The end behaviors are the same. That can't work with an odd degree. I would also point this out. Notice how it says 3 relative extrema. If I have an odd degree, like x to the 7th or x to the 5th, what's the most number of extrema possible for x to the 7th? 6. But then it could go down by 2s. X to the 5th was the maximum number of extrema. and then it can go down by 2s. So can an odd degree have 3 relative extrema? So that's another detail that would break. Right, so we're looking for, can I create a graph that matches those characteristics or not? And the answer in this case is nah. Ain't possible. Alright. What are your questions before we continue with some more learning that will shore up our understanding for that test that we have on Monday? Going once, going twice, and sold. Okay? Remember, we need to pay attention to those details, understanding why. So this is that set of objectives that we just assessed on this understanding check. By the way, go ahead and put all the understanding checks together in the middle of the desk. I'm going to collect and make scans while we start this lesson. So all understanding checks with notes in the middle. Make sure your name is on it. So what were our objectives yesterday that we were assessing right here? That we can what? I hear somebody saying it, but I need someone to read louder. So identify the maximum number of x-intercepts, the maximum turns or extrema, and the in behavior. What else?
Did you already put this in?
Yeah. What else are we looking for here? Oh, that was it. And in behavior. Please notice, right, what we are, you completed that? Please notice what we are trying to base this on is simply the, where's the understanding? Based on the equation, right? We explored the patterns from the equations to the, the equations to the graph yesterday. And so we're trying to make sense of what these sketches could look like just based on the equation, or the graphs could. And what is the fundamental idea that is driving everything we're looking at? Do what? Fundamental theorem of algebra, which says what key concepts? The degree is equal to the number of roots or zeros. Okay, so that degree matches the number of roots or zeros. This allows us to the first is more than enough. Sorry. Okay. The degree matches the number of roots or zeros or solutions. Some of those may be multiple, some of them may be complex, but that's going to play heavily into what we do today. We're ready to check your understanding. Please note here, like, all I'm looking for is example of a polynomial function y equals 3x to the 4th minus 5x to the 3rd plus 2x squared plus 8. Guys, I just made that up. The only requirement was that the degree is even and that the leading coefficient was positive. Now, you could have just typed that equation into Desmos and gotten a sketch of that graph, right? I will point out, I don't know exactly what this looks like, but some things that I would definitely know is that it could have up to how many x-intercepts? 4. It could have up to how many turns? 3, and the end behavior should be going in the same direction. That's all I'm looking for you to summarize here. That's what you need to be paying attention to. We don't have a ton of time to go over this, so we're going to jump to the next part of the lesson. So page 196 in our textbooks. Go ahead and get the books out. Yes, sir. Say again. Oh, yes, sir. Yes, sir. You probably also need the task from yesterday, don't you?
Yes, sir.
I can want to.
Let's rephrase that. There you go. Where are the rest of the brush? You this. Jose, you need this. Traylon, you need it as well, but I'm gonna have to print some more out, because I don't know where. 196 is still on the board. Yeah, still volume 1. You what? Why not? Okay.
I'm trying to hear this.
All right. So at this point, we already did this part yesterday. Remember, we sketched it out here. What we realized was if we have that even degree, the end behavior is the same. But as the power increases, what happened in the middle of that graph? It got flatter, right? It flattens out towards the middle, and we talked about this briefly. Oh, and towards the sides it got steeper, didn't it? Because if I look at y equals x squared, right, and I do 2 squared, what do I get? 4. And if I do y equals x to the 4th, and I do 2 to the 4th, I get 16. And if I do y equals x to the 6th, and I do 2 to the 6th, I get, what is that, 64. So, notice at that same input of 2, what's happening to the y? It's going way up, right? Very quickly as well. But that means also that if I have 1/2 squared, then I get 0.5. No, don't let me lie to you like that. 0.25. If I do 1/2 to the 4th, then I get 1 divided by 16, which is, yeah, that would have been, sorry, 1/4, which is about 0.25. That's about 0.0625. Notice that same input had a way smaller output. What are these getting closer and closer to? 0, which is why in the middle there it's what? Flattening out. The flatter it is, the higher the multiplicity of that 0. So hear me clearly on that again. The flatter it is, the higher the multiplicity of that 0. Technically, in this case, the only 0 is x equals 0 with what multiplicity? Multiplicity of 2. Whereas this has the same x equals 0 with what multiplicity? 4. And this has x equals 0 with what multiplicity? 6. So as that multiplicity of the 0 increases, the flatter it gets at that 0. That's what we would want to notice, and the steeper it gets around it. And that was the answer to 199, which we already did. Okay? Oh, we talked about 199 briefly. We should have. It gets to 0 more quickly, is what we said yesterday. Huh? Yeah. Yesterday, and so like you can have a note, so write a note about that on 199. You could also just say, as Grace did, it gets to 0 more quickly, which is exactly what it's doing. At the same input, it's getting closer and closer to 0. I don't even know what 1 divided by 64 would be. It's probably about 0.01 something. But notice that's way closer to 0. What is it? Oh, 199. So take your notes on that while I make scans of your understanding checks that you did. And then we'll get back to the notes from the book. And hopefully get to vertical surfaces soon. What is that sound?
Oh my gosh, M1T3.
Alright. Okay, so please pay attention to this. We are going to jump from this lesson 1 in the book to lesson 3. So we're bypassing lesson 2 completely. I don't like the way the book does it, and we also don't have the time for it. So we're jumping straight to lesson 3 from where you are. Okay, so going forward, right? I'll have to look at see what page it is. Keep going past that. Keep going past lesson 2, 225. There we go. So page 225. Now, what was I going to say? Oh, by the way, I realized after y'all's class during second block yesterday that I completely lied to y'all about one detail in the study guide. The first page of the study guide is Module 1, Topic 2. The second one is Module 1, Topic 3. So if you go to the book to get notes, push them back one, right? So the one that says Module 1, Topic 3 is actually Module 1, Topic 2. And the one that says Module 2, Topic 1 is actually Module 1, Topic 3. So, Jose, that under the study guide I gave you earlier, so push them back one, just so you know where to go look for information in the book. And Treyon, the same thing with that study guide I gave you. Okay? And I will be uploading the solution to the study guide today. Yes, ma'am. You don't have your book. You have to live on with somebody. Okay? Alright. So it's page 199. So, where it says on the study guide, Module 1, Topic 3, what it actually is supposed to say is Module 1, Topic 2. And where it says Module 2, Topic 1, it should say Module 1, Topic 3. This is incorrect. This is the correct. Okay, so on those study guides, it should say that instead of what it does in the top right-hand corner, just so you know where to look in the book. Raise can pi. Marcus, Kate. Trying to turn anything in or just take notes? Tyson, Naisha, Alright, getting back to where we are in the book, if I can find my... Anybody see the clicker? Did I just use it? That's why I can't see it. There we go. Alright, so, two quick things. We're going to talk about applying polynomials to real-world context. Higher degree polynomials can actually model real-world situations really, really, really well. Because the higher the degree, the more you can account for variation. So we're going to look at that a little bit, but we're going to focus on furthering our understanding of key characteristics with different degree polynomials. So if a teacher or anybody else ever asks you about key characteristics or key features of a function, what are we talking about? What are the key things that we should be able to identify and describe? Domain and range. What else? End behavior. The extrema. The x and y intercepts. And the last one that we're not going to have a ton of time to talk about right now is that increasing and decreasing. We're going to refer to it. It's not something I'm going to assess you on, but it is something to be aware of. All right, so here we are on getting started. This is on page 227. There we go. All right, so we have this study here. So we're talking about math, the real math world versus the real world. So I want you to notice, right? We have all these different points on this graph. They're kind of scattered around. That's the data from the actual study. And then what we do in statistics specifically is we figure out a function that can model that data or go through that data pretty well. What type of function did these statisticians or scientists use to approximate that data? You can look at it in the equation, you can look at it in the shape of that graph. It is a polynomial, which type? Is that quadratic? Why not?
What's the fourth degree called?
Okay, so the highest degree is not 2, it's also not a parabola, can't be a cubic because it's not a third degree, so say that again.
What's the fourth degree?
So one thing I need y'all to hear me clearly on is you can just call it a fourth degree polynomial, right? Like that's an acceptable thing. The highest power is 4, it's a fourth degree polynomial. There is a name for it, and it is called a quartic. Okay? So the name is a quartic polynomial, but you can also just call it a fourth degree polynomial, and that would be perfectly acceptable as well. So a fourth degree polynomial is in fact called a quartic. Now, this though is where the rubber meets the road, and we got to look at the real world versus the math world. Notice right here, A says what is the domain and range of the study. So if I'm looking at this study, what would the domain be? And I will say, is it going to be able to see the values for the study in the table or in the graph? Maybe the graph? If I'll say literally the table is just the study, right? See how we can see individual points for the study there? So what they did is they were looking at, what is it? The glass frog's fertilization habits. So they performed a study and recorded the average number of frog eggs over the span of 44 months. So, what's the domain? In general, what should we think about every time we see domain? The x or the, what's the other word for that, huh? Say that one more time. Okay. It's a certain type of value. It's the x, or x is always known as the, say again, inputs. Right? Remember, x are the inputs, right? They're the independent variable in terms of science. So what would the domain be? What are the values for the study for my x or my inputs? So the number of months, so what are the values for the number of months? Say again. Say average. So remember, so you can average them, but when we say domain, what we mean by that is every single possible value. So when I look at this, the months of the study, where does it start? At what number?
In 19.
Does it start at month 0?
I just talking about all these.
You good with that?
Oh, sure.
You see how that would be my x or my input? I got you. But remember, that's my dependent or my y, right? And it's starting at month 0. And notice here, the graph, doesn't it start also at month 0, right? This graph is just a representation of this table. And so what's the maximum number of months here? Okay, 43 in the table, but I don't know why they didn't do a 44th, but it does say 44 up here, so I would accept either. But here's the thing, I could get anything in between. So what notation do we use to indicate the beginning, the end, and everything in between? Interval notation. And how do I do the interval notation?
Why?
We use brackets or we can use parentheses. What number always comes first? I will say brackets for this one, and I'll explain more later, huh? Okay, but what is the, say again? 0. Remember, domain is only x, but we always put what value first in interval notation? Not always 0, but always the minimum value, comma, maximum value. It doesn't matter what you're discussing. If you are using interval notation, you always put the minimum, then you put the maximum. And so what was the minimum number of months in the study? 0. And then what would be, I put a comma, and then what's the maximum? 44 or 43, either one. I'm going to go with 44. Boom, there's my domain. And remember that comma literally means that it's anything in between. It's an interval, right? It's everything in between. And I think it does ask us to explain what it represents. So, when I look at the context of this study, what does that 0 to 44 talk about? That's the months of the study, right? Month 0 all the way to month 44. What about the range then? It'd be the y values or the outputs, right? So what is the minimum y value? I was gonna say, just because this is the starting does not mean it's the minimum. We have to look through.
It's not right.
I was say there's 108. Does anything go below 108? Think that's it.
108.4 actually.
Oh, okay. Okay. 108.4, that's the minimum. Comma, what's the maximum?
15,966.9.
Okay. So I think that is the maximum. Did anyone see anything larger than that value?
You definitely didn't.
15,966.9. But what do those numbers mean in the context of the study? The average number of eggs that are laid or fertilized or something like that. So average number of glass frog eggs. We can just leave it at that, right? So we could have anywhere from 108.4 glass frog eggs fertilized all the way up to 15,966.9 glass frog eggs fertilized. Now, notice the difference between A and B. What is B asking about in terms of domain and range? Domain and range of what? Not for B, is asking for the function. Notice this is my function that I'm using to model that data, but notice this function continues up and to the left. It continues up and to the right. Notice somewhere in here is the minimum number of eggs laid, but you see how this function actually goes below that here? Right? Functions will never perfectly model the data, but it'll get close. And so we need to consider the difference in the domain and range of a study versus a function. So what would be the domain of this function? Remember, domain is the set of all what? X values, set of all inputs. Looking at that graph, what is the lowest x value for the function? Again, the lowest x value. Remember, what direction is x? Left and right. So Tyson, I heard you say 0. But notice with the function, you see how it has that arrow there? So it is going up, but remember I want domain, which means I need to focus on left and right. So it's also going to the
left.
It's going up and to the, and which of those do I care about for domain? Going to the left. So what's my lowest domain value? Negative infinity. Just as a heads up, with infinities, you will always use parentheses. I'll explain why next unit, but for right now, domain you always, or infinities, you will always use parentheses. What's the maximum domain value? Positive infinity. Okay. Notice it goes up, but it also, and more importantly here, goes to the right, and it never stops going to the right. There's my domain. Now, there is a way to find the minimum here for this graph. We'll do some of that in a second. Does anyone remember how I could find, first off, where is the minimum y value for the graph? For that function there? At an extremum, which one? Because I got 3 of them.
The first one?
That's the absolute lowest y value?
Yeah.
Sure?
It's a joke. Yeah.
See that gets a little bit lower?
Yeah.
What feature on the calculator could literally tell us what that point is?
The graph.
So we analyze the graph, and then there's an option for a what?
Minimum.
Minimum. We'll do that in a second. But for now, let's just estimate what that range is. The range would be, I don't know, maybe negative 3,500. Notice, does it ever go below that minimum right there? No. So that is what we would call an absolute minimum that we'll talk about in a second. And what is the maximum y value?
Oh, no,
It's what? Positive infinity. It never stops going up. It keeps going and going and going and going. And so the maximum for the range would be positive infinity. And notice with that graph, because that curve continues forever, do I have every y value between that negative 3,500 and positive infinity? Okay? We want to recognize that with a curve, there's a point that has a y value, there's a point that has a y value, there's a point, there's a point, there's a point. How many points are there from this negative 3,500 all the way up? Not just a whole bunch, it's how many? Infinitely many. The way we get a smooth curve is that there's actually infinitely many points from one point to another. Doesn't matter how far away there are infinitely many away from each other. We're not going to go through C through F because we need to get to other stuff, but I will point out to you what we can do with one of the reasons why we like models like this is by knowing the domain and the range. If the study lasted for 50 months, 50, was that my input or was that my output?
Input.
That's an input, right? So could I substitute that 50 in for x in this function and get an output value?
Yeah.
That's why we want to develop models, right? I wish we had more time to explore this, but that's the whole point of these types of functions is that when we can model real-world data, that we can actually substitute inputs in and make predictions, right? Making a prediction about the future is a very useful skill. Okay? So that's all we're going to talk about there. So notice the key out of this is paying attention to domain and range, because those are two key terms we're going to talk about later. Okay, so here's where we're going to work with this a little bit is activity 3.1. Go ahead and pull or get a calculator. So one person per group, go grab calculators. Once you get a calculator, type this equation into a graph for me. Yes?
Hey, give me 2.
So grab a calculator, type that equation in quickly. David Z, let's go ahead and do it.
Aisha, huh? How you doing yesterday? Oh, never mind.
Guys, I need you typing this equation into the calculator. We should know how to do this. Z, have you typed that entire equation into the calculator? To graph it? Huh? You don't know how to create a graph page. Hit escape. Go on home, hit 1 to create a new document. Remember the caret symbol? Hey guys, if you need an exponent other than a square, that little caret symbol next to x squared allows you to do any exponent. You see next to the x squared, the little caret symbol? That'll allow you to do any exponent.
Where's this equation? That's not just a question. What made you think?
You know it's in the book, right? Guys, this is the same equation that's in the book at the top of the graph. Nope, turn back to that page. I'm getting started. At the top of the graph, it has the equation there. And what I would do is I would use the same scale that the graph has in the book. So 0 to 50 in the x, negative 5,000 to 20,000 in the y. So window settings, 0, 50, negative 5,000 to 20,000. And notice that gives me a graph that looks pretty darn close to what they have in the book.
What you put for watermelon and watermelon?
Look at the graph in the book. See how it has those? So I just did that.
Oh, wait.
Nope, that's fine. It only matters when you have parentheses in there, and I don't know why, but.
Shut up.
Gotcha. So, I agree with you. Come on. Hold on, go back to. Check your equation, make sure you typed it in right. Remember, I just did 0 there. And then I did negative 5,000 in the y. You typed something in wrong. You see right there where you missed the, I think it's a plus. And also, yeah, that should be in the exponent.
Would you show me why?
Minus, was it a plus here? Be careful. That should be right. Okay, now change your window settings once you have that going. I think you should have, you forgot your X right there on 540.
We change our window settings to.
Just use the settings that it has on the graph on page 227. You see where it has, I think it's 0 to 50 in the X. So like look at the axes, yeah. What are you confused about? No, menu, hit the menu. Down here. Go to window settings, go to window slash there, window settings.
The first one.
Go to number 1. You're there. And then, just like that, please.
If I just passed it, then
Miss Kennard, I did something wrong.
Okay, this last one and then I'm getting started. 0 to 50. Remember, the X is from 0 to 50. the y goes from negative 5,000 to 20,000. All right. We're starting. Okay. So here's the point that I want to make about the calculator here is number one says use graphing technology to determine the x-intercepts of the function. We're not going to worry about the second question. How am I going to use this calculator to find the x-intercepts? Because there's a beautiful part that, man, I got this graph here. What am I going to do now? I'm going to hit menu, and I'm going to analyze my graph. And I don't see the word x-intercept, but what do I see? No, not intersection. No, not integral. Zeros are the same as x-intercepts. Intersection is specifically between two different curves or lines. We want a 0. Now, please pay attention to this. In the left-hand side there, you see I have two x-intercepts pretty close together?
Yeah.
So you can only get one at a time. So when it says lower bound, I need my line, my vertical dash line there to the left, but then upper bound, I'm just barely going to go to the right so that I'm not to the right of both of them, and then I'm going to hit enter. There's my first 0. And I'm going to do it again until I get all 4 of them. Okay. So at least get 1 or 2 of those. We're going to talk through this. You got to try to find those zeros. There you go. Okay. Anybody not able to find any zeros? Yeah, so if they're ever right next to each other, move your hand on the cursor so it's right over one of the numbers. Hold down the hand until it closes, and then you can move the coordinates around. So you can always move different things like that. Huh? So you have 2 of those 4. Do note you would want to get the other 2, but yes. You don't have to, but like for right now, I just want you to know how that we can do that. Okay? So, eyes and ears up here. Here's what I want to point out. Please remember, we're supposed to have a 0 in x-intercept. These, for me, actually very clearly had zeros. Did some of y'all get this, though, instead of a 0? Or something like that? So, where in the world is that coming from? Because that doesn't look like a 0, does it? Does anyone know where that comes from? Has anybody ever seen this E before?
Yes.
Do you know where it's from?
It's like whenever you have too much stuff like that.
Kind of. This is scientific notation. You hopefully have seen it written a slightly different way, where that E is understood to be times 10 to the -8th power. That's scientific notation. And hopefully you remember that when we have a negative exponent, that means repeated what? Say again?
Addition.
So remember, multiplication is repeated addition. Division is repeated subtraction. An exponent, though, is repeated what? So a positive exponent is repeated multiplication. What's a negative exponent? Repeated division. So what I'm really doing is -2 divided by 10 to the 8th, or -2 divided by 1, 2, 3, 4, 5, 6, 7, 8. Anybody know what that's going to be really darn close to?
Yeah.
0. It's just a calculator error in this. That is 0. So if you ever see E with a negative exponent, that's really close to 0. Okay? So that's what you would want to be aware of there. That is still a 0. You can literally see the point as an x-intercept. It's just really close to 0. Now, it does ask in that question, what do these x-intercepts mean? We do want to think through context. So like right here, what is our x in the context of the study? 41.3 what?
3 months.
41.3 is rounding.
Oh.
41.3 what? Months into the study, there are 0 what? Frog eggs being laid, right? So we want to think through that X and that Y, we want to think through that context. When we see a point, those X and those Y's mean something. It's not random, okay? So that's one thing that we can do with these calculators. State the end behavior of the function. Right, so number 2, look at your graph. What would the end behavior be? By the way, just note, did on graph, we ain't going to sweat it too much, using 0. We need more than just that. No! Try turning it on back again if it doesn't work. It's what? Okay, so first off, the end behavior will be the same. It's an even degree, but what is the end behavior? As X approaches what? What do you say? Okay, so as X approaches negative infinity, remember, X approaching negative infinity is going to the left. So as X goes to the left, what's Y going towards? Well, it's going up to positive infinity. That's the end behavior here. Yeah, 228. Let me get my pins in here, thank you. Can you get that pin back from you afterwards? Okay, so then please remember though, how many ends does this graph have? 2. So what's the other end behavior? Not quite. There's one big difference. As what? X goes towards positive infinity, meaning as it goes to the right, Y goes towards. Is it going up or down? Look at the end behavior. There we go. So that's what our end behavior would be. So in the terms of the study, do those numbers make sense? Thank you. Why not? What do you mean by that? Can you have infinitely many eggs being laid and fertilized? Thank you.
Sure, if you wanted to.
How many frogs have you ever known that laid infinitely many eggs?
Okay, we don't look at frogs, baby.
Never met a frog?
I'm guessing it's a problem.
I was gonna say. I want to let you in on a little secret. Nothing's ever reached infinity. Right. Listen, tell you what. Just take, like, watch video, take notes on it, and I'll use your test to assess those skills. All right. Now, let's talk about number 4. Please listen. This is one of the last skills I'm going to really show you, but this won't be on your test. It will be on your next test if you're a junior. It says, describe the intervals when the frog's egg population is increasing. So one thing to be aware of is this. Where would a function stop decreasing and start to increase?
At a term.
So at extremum, right? Specifically, which extremum would have it stop decreasing and start to increase?
Negative.
So it stops decreasing and it starts to increase? So at a minimum. At a maximum, it's going to stop increasing and start to decrease. Hear me very, 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 very clearly on this, though. You will regularly hear people say intervals of increase and intervals of decrease. What they most accurately mean, though, are domain intervals of increase and domain intervals of decrease. So when we say increase and decrease, what do we mean by increase and decrease? That's the what? What? When I look at a graph, what's increasing and what's decreasing? How do I know this is increasing? What? Right, so if we're talking about up and down, we're talking about what? We're talking about the slopes only for lines, kind of technically. You'll learn more about that in the future. But if you go up and down, we're talking about y values, right? So when we say increase and decrease, we're talking about y values. However, what type of intervals are we looking at? Domain. So the interval you write will only be what type of values? So remember, the y values are increase, decrease, but I'm writing a domain interval, so I'm going to write about the x. So when I ask for a domain interval, we're going to write an interval based on x. So an example of this, get rid of these so we can see things more clearly. So notice, remember, you can do analyze graph and do a maximum. There's a maximum. Here's a minimum. And here's a minimum. So there's other places that we can see this, but notice how it starts to increase from here and it stops increasing up to here. So one example of a domain interval of increase, where's the minimum? Where does it start to increase? Remember, we want a domain value, so we're going to use 5.75, rounding. Where does it stop increasing? Every time I teach this, students are tempted to use the y values. But what type of interval are we writing? Domain. We are talking about the y's. We are saying that the y values are increasing, but it's on this domain that the y values are increasing. So what's an example for a domain interval of decrease? 21.5 to what? That's it. The y values are decreasing and we're writing a domain interval for that. So there are other intervals of increase and decrease, but that is the clearest examples that I could show you quickly with the amount of time we have left. Last couple of details. You've learned about minima, you've learned about maxima, zeros, in behavior, general shape of a graph. But here is a last detail that we need to note. The absolute maximum is the highest point in the entire graph. So is there an absolute highest point for the glass frog eggs? Does anyone see one?
A real one?
Say again?
A real one? A math one?
So a math one, right? So we're talking about the function, not the study. For the function, is there an absolute highest point? But so can you ever reach infinity?
Yeah.
So infinity can never be a maximum or a minimum. Say again?
Isn't it extreme for the television?
You see this extremer right here? But here's the question. Are there y values higher than that? Because it absolute maximum has to be the highest point for the entire graph. So are there y values higher than that? Because it keeps going. Forever and ever and ever, right? So in this case, guess what? There's no absolute maximum. Okay? There's no absolute maximum, but is there a relative maximum? I believe this might be on the next page, sorry.
Yeah.
This is on page, under number 5. Are there any relative maximum?
Yeah.
Yes? That point Remember, relative just means it has to be the highest for its what? Its area, its section. It's where it stops, what?
Stop increasing.
Stops increasing and starts to decrease. It does that right there. So there's a relative maximum at 21.5, 14,541. So a relative maximum at 21.5, what was it, 14,000?
I think it's 61. I might be wrong.
541.
Oh, wow, oh.
It's all good. By the way, I'm going to erase this comma. Does anyone know why I'm not putting this comma in here?
Makes it like a 3.
It looks like there's 3 commas. So we don't put commas with thousands and millions in points because you need a comma with that point. Same thing with interval notation. That's why mathematicians around the rest of the world don't use commas for the thousands place. Yeah. So there's a relative maximum, but there are no absolute maximum. Is there an absolute minimum?
Yeah.
Where would it be? This right side over here?
Yeah.
So first off, is that a relative one?
Yeah.
Yes. Are there any y values lower than this point? So it is also an absolute. A point, or you cannot have an absolute if it's not also relative. Okay? So absolute minimum at, what's that, 38 point, say 2, comma, negative 2,807. And there's a relative minimum at 5.75, comma, negative 311. And at that point, right? So we have multiple relative minimum, but can you ever have more than one absolute minimum?
No.
Not unless it has exactly the same y value. But that's very, very, very rare. So, with the last couple of minutes that we have, I want to point something out to you. Think about your cubic functions or your odd degree functions. We've talked with odd degrees about the maximum number of relative extrema, or terms, but can you have an absolute extremum with an odd degree? Can you have an absolute extremum with an odd degree? If it's always going down to negative infinity and always going up to positive infinity because of that opposite end behavior, there's no way to have an absolute. But you can have some relative. When I look at an even degree though, if the leading coefficient is negative, you can have an absolute what? If the leading coefficient is negative and it's going down on the end behavior, it's an absolute maximum. If the leading coefficient is positive, you can have an absolute minimum. That's what we want to notice. Now, I want you to hear me very clearly on this. That's too much information to just memorize. But if you can remember the shapes and the end behavior and sketch these things out, you can visualize it. This would be on a non-calculator portion of the test. However, you can always sketch it out based on those features that you know. So we will have a test on Monday. I apologize that we did not get to do more. We will do some more after that test. However, seniors are gone after next week, and I got to get those tests in and graded. I did not update that closing slide. Test on Monday. I will post solutions on Schoology for the study guide, so be on the lookout for that. I should have it up today. I think I've passed out everything that I needed to pass out. Questions, comments, or concerns? Have a fantastic weekend. Take the time to study so that you can maximize your learning. Sir. For the last assignment? Okay. Finished with everything? Okay. That would be an example of an odd degree with a positively equated distribution, right? Notice that the end behavior looks like a line with a positive slope. That's how I always think about it.
So does that what the polynomial function not